far, we've been looking at accessing archival data one object at a time. This approach is fine if you want to search for information in the archives on a small sample of objects, say a few tens or maybe a few hundreds of objects. But once you go to sample sizes of thousands and tens of thousands of objects, this way of getting data from the archive becomes a very slow process. In such a situation, it is better to write a program which can automatically access the data that you are interested in. The module or the piece of code that allows you to do that is called AstroQuery, and it is a Python language package that will provide you with this capability. It is very easy to code in, and it contains a number of sub packages for each data repository. So, there will be a separate sub package for accessing SDSS data, there will be a separate sub package for accessing catalogs in Vizier and so on. But before we go to AstroQuery, let us first try to understand what Python is all about. So, Python is a programming language which happens to be the dominant language used in the analysis of astronomical data. It is the most popular language to access data in astronomical archives. It is an interpreted language with a large number of sort of auxiliary packages, which are referred to either as packages or modules, which are available as standard libraries and as third party supplied packages. It provides its users with a complete ecosystem for handling astronomical data. So, if you are not a programmer and you wish to learn just one programming language, then Python should be your choice. It also helps that Python is a language that is very easy to learn and perhaps more importantly easy to read. Sometimes what happens with other programming languages is that you might be quite good in writing code in that language yourself, but if you are handed over somebody else's code and asked to modify it, it becomes very difficult to understand. But Python is such a tightly structured language that it becomes very easy for you to understand not only your code which you may have written many years ago, but also other people's code that you need to look at and modify. In order to use AstroQuery in a programmatic way, you will definitely need to learn Python. We are not going to teach you Python here, but there is a detailed course available online which is specifically on using Python for astronomical data analysis. And I have given you the URL here. Please go and download the course. You can watch the videos, you can download PDFs, and you can also download code snippets that are used in the teaching of the course. Python is very widely used in all of astronomy. Here I give some examples of the usage of Python in optical astronomy. One of the most widely used packages for optical data analysis is a package called IRAF, Image Reduction and Analysis Facility, which was developed several decades ago and is still in use. What has now happened is with the advent of Python, IRAF has been wrapped as a Python package. This means that you can use any IRAF command from within a Python program, and this is done using a package called PyRAF, which wraps all of IRAF and also provides you with additional Python only routines. Similarly, the ESO telescopes used a data reduction software called MIDAS, which has been similarly wrapped and is available through Python in the form of PyMIDAS. Access to FITS file was also wrapped with a program known as PyFITS. and there are several other packages listed here below, which tell you that Python is used in a wide variety of situations, right from solar system ephemerides to doing the software reduction of data from the Large Synoptic Survey Telescope or the LSST. Here are some examples now from radio astronomy of Python usage. So, one of the biggest data analysis packages in Python now is called CASA, and it is basically a set of C++ libraries which forms the core of CASA, which is used to be called apes++, and it has been wrapped now with a Python package which is called CasaPy. So, you can now do all radio astronomy data reductions from within a Python based system called as CasaPy, and it is the default system for reduction of data sets from JVLA and ALMA, and therefore is very well supported by its developers. An older package used for radio data analysis was called apes, and that is still widely in use. And there is now a wrapper for apes which is called parseltongue, which allows you to call apes tasks from within a Python program. The ERAM data analysis package called GILDAS has also been wrapped. There is a similar package for the Laboca instrument on Apex and other bolometers. There is also an increasing trend in radio astronomy to use a Python based system for building monitoring and control software for telescopes, and this has been pioneered for the CAT7 system. The control and monitoring system for the CAT7 telescope in South Africa was developed in Python, and that will now be extended to the control and monitoring system of the Meerkat telescope. Pulsars are an important area of research in radio astronomy, and one of the most widely used packages for pulsar search and analysis, known as Presto, has its most recent routines all written in Python. So, as you can see that in a wide variety of domains, be it optical astronomy and radio astronomy and also X-ray astronomy and other astronomies, it is now extremely common to use a Python based package for all kinds of work. So, let us now look at the main Python modules that are important for astronomy. If you look at Python itself, the core language is very poor at processing arrays. Okay? It is very slow because it was never designed for fast numerical processing. So, in order to add that capability, a package called NumPy was developed some years ago, and it provides very fast array processing capabilities in the Python language. For science, one needs a number of scientific and mathematical packages that allow you to do things like obtain roots of equations, solve differential equations, invert matrices and things like that. And all those capabilities, all that functionality is provided in a package known as SciPy. It is a very large package naturally because it provides so many different capabilities, but you can get the solutions to most of your numerical and scientific computing problems somewhere in the SciPy package. Python by itself does not have any standard library for plotting figures. That capability is now provided by the package matplotlib, which is now the de facto standard plotting library for Python. It is very widely used, it is very powerful, very well documented. Its syntax is very similar to the syntax of MATLAB. So, if you are familiar with MATLAB and know how to make plots in MATLAB, learning matplotlib will be a matter of minutes for you. Now, coming to core astronomy, the most important package for astronomers is something known as AstroPy. It contains a lot of software that is relevant for astronomers, and it contains basically a set of core packages which provide the core functionality, We will look at that in a minute. But it also provides dozens of affiliated packages that operate well with AstroPi. Okay. And last but not the least is a package called AstroQuery, which provides tools for querying online astronomical data sources, right. So, from the point of gathering data from astronomical data archives, AstroQuery is the one module that is most important. It is also an affiliated package with AstroPi. AstroPi itself is now fairly large and provides a wide range of capabilities which are listed here. There are a set of packages related to data structures and transformations. It deals with constants, units and quantities, handling of n-dimensional data sets, data tables of various kinds, times and dates and interconversions between say the calendar date and the Julian date and so on, astronomical world coordinate systems, different kinds of modeling and fitting routines are all available. There are a number of tools that allow you to do files I/O and communication, reading of FITS files, writing of FITS files, same thing with ASCII tables and the VO table XML format and also the SAM format. So, the kind of capabilities that we saw in interactive manner in Aladdin and TopCat etc., can be accessed programmatically very easily using AstroPi. There are also some utilities for computations, for example, for cosmological calculations, convolutions of various kinds, various transforms, Fourier transforms and so on. A upcoming module for data visualization, which is still not very advanced, but one hopes that in the days to come it will grow more capable. There is a nice package called astropi.stats, which allows you to compute statistics on any data that you are looking at. Besides that, there are some nuts and bolts packages related to the registry of AstroPi and its configuration system, its logging system, its warning system and so on. So, let us now move to AstroQuery. AstroQuery, as I mentioned previously, is an AstroPi affiliated package. What that means is that it is not part of the core AstroPi package, it is a separate package by itself, but it is guaranteed to be interoperable with AstroPi. So, for example, if you retrieve some data with AstroQuery, then you will be able to use, for example, astropi.stats on that piece of data to gather statistics about that data. Similarly, if you read a file or a catalog in AstroPi from your own hard disk and you want to send it to a web service for an online search, then you can pass on that piece of that catalog or that table to AstroQuery and it will send it over to the online service and query and run the query that you wish to. The way they have partitioned things is that each web service has its own sub package. Okay. So, there will be a separate sub package to access Vizier, there will be one to access SDSS, there will be one to access the ADS and so on. So, let us look at some of the AstroQuery modules that are available. This is the list of modules as it stands today, and there are several pages which we will go through now, but there are many more that are in the process of being added. So, as one goes into the future, one hopes that even more and more data archives could be directly accessed from within an AstroQuery program. Simbad is a database that it is an online database maintained in France, which originally used to gather data about stars, but now does other objects as well. It provides some basic data and cross identifications, bibliography and measurements for astronomical objects outside the solar system, which means stars and galaxies of various kinds. The Vizier sub-package of AstroQuery allows you to query the 17,000 plus multi-wavelength catalogs that are hosted in the Vizier system. ESA Sky is a portal. It allows you to access a science driven discovery portal which is run by ESA. The IRSA image server program interface provides access to a number of infrared surveys like TUMAS, WISE and the Palomar transient factory. IRSA DUST gives you maps of galactic reddening based on 100 micron data from the IRAS survey. NED is the NASA extragalactic database. It contains a large amount of information about extragalactic objects like galaxies, and there is a lot of multi-wavelength data there, both collected together from various surveys and from research publications. AstroQuery gives you access to IRSA, which is the NASA IPAC Infrared Science Archive, and which contains science products for all of NASA's infrared and sub-millimeter missions. The UKID SS package gives you access to a near infrared survey carried out with the UKID telescope in Hawaii. So, there was a survey called the UKID Infrared Deep Sky Survey, and there are JHK images of a large area of the northern sky. There is a sub package called MACPIS, which stands for the Multi-Array Galactic Plane Imaging Survey, and contains radio data at 2 frequencies of the galactic plane obtained with the VLA. The NRAO package gives you access to the science data archive of NRAO. The Bezencom package gives you models of stellar population synthesis in the galaxy. The NIST package, maintained by the National Institute of Standards and Technology, gives you access to atomic lines databases. This is very important if you want to look for specific atomic transitions in your spectra, for example. You will need to know where all the lines are, and you can get them from here. Fermi gives you access to the Fermi Gamma Ray Telescope archive. SDSS gives you access to the entire Sloan Digital Sky Survey data, including images, spectra and spectral templates. Alpha Alpha was a survey carried out with Arecibo, and that can be accessed. It is an extragalactic H1 radio survey that can be accessed from within AstroQuery. Just like the Hubble Heritage Archive that I mentioned previously, there is also the Spitzer Heritage Archive now, which contains infrared data products from the Spitzer Space Telescope, and that too can be accessed from within AstroQuery. Lambda is a atomic and molecular line database, again various radiative transitions, energy levels, collisional rates, etc. For the astrophysically relevant atoms and molecules are tabulated by a group at Leiden, and therefore, it is called Lambda. It is available through AstroQuery. OGLE is an ongoing gravitational lensing experiment, and it gives you a lot of data there from on interstellar extinction in the directions of the galactic bulge. Splatolog is NRAO maintained molecular radio and millimeter line list service. So far we have looked at data, but there are also simulations that can be accessed now through AstroQuery. So, there is something known as the CosmoSim database, which provides results from various cosmological simulations like the Multi-Dark project, the Bolshoi IP project and the CLUES project. Besides this, you can gain access to the ESO archive, the ALMA archive and the Gamma database. Gamma is a galaxy evolution survey that has been carried out with many different telescopes, including the Hubble Space Telescope, and of course, the NVAS archive. So, as you can see that through a single module, it becomes possible to access any sub package. So, let us now go and try to look at a short demo of how simple it is to access data in AstroQuery. I am going to show you only one example, but if you go to the AstroQuery documentation, you will find that there are numerous examples for any kind of data set that you like. So, for example, I am going to show you how to access data in Simbad, but the process for accessing data in SDSS or in TUMAS etc. is very similar. The syntax is very similar, the APIs are broadly consistent with each other. So, if you learn how to do it for one data repository, it is quite trivial to extend it to another data repository. So, I have just opened a terminal in which I am going to start the Python interpreter. So, there are several Python interpreters available. I use a very user friendly one called IPython 3. When I type IPython 3, it shows me a prompt. So, I am now in the Python interpreted language. What I am going to do now is just show you the code that we are going to run. Let us now go over the code line by line, and I will run each line after I show you what the code means. So, the first line simply tells the shell that I want you to use the Python 3 interpreter when you run this program. So, this is useful when you want to just run the whole program at one go, but we are not going to do that. We are going to run the program one line at a time. The first thing I do is I type from astroquery.simbad import Simbad. So, what does this tell Python? It tells Python that from this particular package astroquery.simbad, I want to import a function named or a sub package named Simbad. Okay. So, I just press return, and if there is no error, one assumes that things have gone through. So, what has happened now is that in the namespace of Python, we have actually imported the module called Simbad. Now, the second one is actual running of the query. So, what does that line say? Result table is equal to simbad.query object M1. So, what it basically says this line does is it sends a query to the Simbad service saying that there is an object which is referred to as M1. Okay, this is of course the supernova remnant, which is referred to as the Crab nebula, Messier object 1. I want you to send me what information you have on this object. Once that information is returned, it gets stored in a table which is referred to as result table. So, let us run the query. So, many things will happen in the background. A connection will be made to the Simbad database. This query will be sent. The results of that query will come back and they will get stored in the result table. So, all this has happened in a very small fraction of very small amount of time. And now, in the result table, we have now the information that we wanted from about this object. So, there you go. So, it tells you what M1 is, what is its main ID, what is its coordinate, the right ascension and declination are indicated here. and some other basic information, and at the end it gives you a bibliographic code. It gives you the name of the paper from which this information has been collected. So, if you wanted more information on exactly how these positions were obtained or all these other parameters were obtained, you would need to go and refer to this paper. Right. Now, let us do something a little more complicated. We change that result table line to Simbad.query object m in square bracket 1 to 9. Okay. So, what this means is use every value between m1 and m9 and send a separate query for each of them. So, ask Simbad for information on m1, then ask it for information on m2, ask it for information on m3 and so on up to m9. These are all Messier objects of various kinds. Wildcard equal to true tells this particular function that you should use wildcards while interpreting the input. So, then it knows that this is not some object called m square bracket 1 dash 9, it is actually to be interpreted as a wildcard. If I say wildcard equal to false, it will work very differently. So, there you go, it sends a query to Simbad, it gets a response and it stores again it in the same result table. So, if I print the result table now, you see that now I have gathered much more information all the way from M1 to M9. They are all of course at different positions on the sky, and even the papers that give you this information are somewhat different, and for every object you get a bibliographic code, a bibliographic reference for more information. So, this makes it extremely easy for us to query almost any database. Remember, we did not even specify what we really wanted. Okay, we just told it I want information on this object. We did not have to specify what is its position on the sky, whether it is a planetary nebula or a galaxy, nothing, just a name. I am going to show you now another program which is very similar to this one. We will not run it here, but I just want to go through the program so that you realize how similar it is to access another archive compared to the Simbad example that we just saw. Okay. So, this is a short program over here that allows you to query the SDSS database. So, the first line is identical, and now we are going to import something called capital SDSS from astroquery.sdss. We need to import one more AstroPy module this time, which is coordinates. This module takes coordinate strings in various formats and converts them into a standardized format which can then be sent to the database that you are querying. The next line, which starts with pos equal to coords.skycoord etc., it basically converts the coordinates that we have given here in terms of right ascension and declination into a standardized format, which is then stored in the variable pos. The next line actually does xid is equal to SDSS query regions pos spectro equal to true. So, this does a large number of things in one line. So, what it does is it sends a query to the SDSS service and tells it I am interested in a region around this position pos. Okay. So, there will be some default region, I think it is about 30 arc minutes that it searches around this specific position, and spectro equal to true. So, which means only return to me objects for which you have a spectrum, right. and then it prints the value of xid, and then of course you may want to get the spectrum, fetch the spectrum, and that is done by this command sp is equal to sdss dot get spectra matches is equal to xid. So, for all the objects that are returned here, so this particular query, if you run it, I think returns only one object, but if you increase the search radius, for example, you could get many objects, and all of those spectra would then get downloaded using this single command sdss dot get spectra. If you wanted, instead of getting the spectra, you wanted to get the images of that object, you would do im is equal to sdss get images, matches is equal to xid, band is equal to g. This specifies that you want to download image for the g band. Note that there is a hash in front of it, which indicates that this is a commented line. So, if I wanted to actually run that, I would need to uncomment that, remove that hash sign, and then it would run. So, as you have seen from these two examples that I showed you, it is very, very easy for you to write and run very short pieces of code in order to gather data from for the objects of your interest. For example, here we have only one object of interest at this particular coordinate, but you could easily put this piece of code into a loop wherein you would read in the first coordinate of the first object in your sample, supply it here, run the query region, download the images and spectra, and then repeat this exercise one by one for all the objects in your sample. So, it is absolutely trivially easy to gather data from everywhere. You can even do cross matches, you can mix and match data, you can download some data from SDSS, download some data from TUMAS, some other data from Fermi, combine it together using AstroPy. There are even modules for you to display all of it together, combine it together into an RGB image, and so on. So, there is really no limit to how complicated you can make your AstroQuery program. There are I have shown you two very short examples of code, but there are more complicated examples in the AstroQuery documentation. I urge you to go to the AstroQuery website and read the documentation. They give you very long examples, 2 or 3 pages long, which combine data from multiple surveys and make plots and things like that. So, I hope you have convinced you that it is very straightforward and extremely easy to access data using AstroQuery, and in fact, once you start using it, it becomes second nature, and it is definitely a very fast and efficient way of gathering data, even when you are doing only a few objects, because what you can do here is that once the data are downloaded, you can systematically classify them and store them in separate files and so on. So, by running a single program, you can gather all manners of information about your sample.